I saw somebody comment. I was indeed at Rickard's earlier. We're getting everyone to come through. Hang on a second. We have our tech team setting all of our stuff up. So yeah, good to see you guys. So first of all, I want to welcome everyone to our channel. I think we might already be streaming on YouTube. Yes, I see Alex Jiang says that you are on YouTube. That means our YouTube has started. So, well, first of all, welcome to everyone. I'm Po-Shen Loh. I am supposedly a math professor at Carnegie Mellon University, except that right now I happen to be in Atlanta, Georgia. That's because, believe it or not, there is a conference happening right now of all the people, not all the people, a lot of the people who run the math camps that lots of high school students go to. You might have heard of a camp called Canada USA Math Camp. I think I might have seen. I think Eli, you were there. Is that right? I saw you there a couple of years. Yeah, yeah, yeah. So, well, it's not that's not the only camp which is here. We actually have probably about 10 to 15 of the summer math camps that many high school students like to attend. Believe it or not, the people who run math camps get together to discuss like how do you run a math camp. So hopefully all the math camps get better. But that's why I myself am going to drop off. But I do want to introduce two people who are going to take very, very good care of this because this is all being run on our live channel. And our live program, if you haven't heard of it before, we find lots of really clever and also very kind high school students, and then we have them live stream in a way that's super engaging, which you're about to see, which uses this thing called chat relay, which they're going to explain to you. But without further ado, I'm going to pass this over to Eli and William. Usually you guys just take over from maybe alphabetical by first name. So I'm going to go back to this meeting, unfortunately, but you guys are in very, very good shape. Have a good show.
All right, thank you, Professor Loh, for the introduction. And hello, everyone else. Welcome to our AMC 10A live solve. Glad you could join us. I am Eli, that's William. And well, I might as well go introduce my co-teacher here. William Hua, on my right, is a senior at Lexington High School. He is also a USAMO qualifier. And outside of math, he enjoys cybersecurity, card games, music, and playing with his pet dog. So everyone welcome my awesome co-teacher, William, for this live solve.
Right, thank you so much, Eli, for the introduction. And in the meantime, I'm also going to introduce Eli. So Eli is a three-time AME qualifier, and he's also got a perfect score on the USA Mathematical Talent Search, which is a very interesting research contest. And he loves to do pure mathematics, especially number theory, and he's taken a lot of graduate level math courses at the University of Connecticut. And he also runs the number theory enrichment program at the students at his high school. And in addition to mathematics, he has the Presidential Scholar Award. And for hobbies, he likes to do music, especially the marimba, which is a percussional instrument. And he even does international competitions where he won awards for the marimba. And other hobbies include cubing, playing ping pong, tap dancing, and also playing chess. So everyone welcome Eli.
All right, thank you, William, for that introduction. And I guess, okay, Professor Loh did mention we should tell you how the chat works, but I think people already get the idea. You send messages to this thing called chat relay, and the messages will appear on our screen as they are doing now. So yeah, good job to everyone who already figured that out. And now I think we'll just get right into the problems. So our first question is 2025 AMC 10 number 3. And yeah, I guess I'll just take this one and William can take the next one. So we have how many isosceles triangles with positive area and side lengths, all positive integers whose longest side has length 2025. Okay, so I'm already seeing there's probably going to be like 2 cases here because, or maybe even 3 cases. We have an isosceles triangle, so that looks something like this, right? 2 equal sides, 1 unequal side. But these 2 equal sides could be the longest, or they could be not the longest, and we have like one really long side and something like this. So there's the 2 cases to consider. The first case is when the longest side is 2025. So that means this side here is 2025. And so is this side, and this side is something else. And the other case is like this, when the bottom side is 2025, and the other 2 sides are something else. Okay, so now we need to like count how many of these are possible, which is pretty weird. Oh, okay, I'll also say there's one more case, which is when all of them are 2025, but that's like an easy case. That's the equilateral triangle. So there's just one of those. And we're fine with that. Okay, in this case, we have 2025, 2025, and I'll call it X. Now, what do we need for this to actually be a triangle and hint, hint with positive area, that's here, and positive integers? Well, there's a very well-known condition for that, and it's called the triangle inequality. And the triangle inequality says that the sum of the two smallest sides has to be bigger than the sum or than the size of the longest side. So what that says in this case is that x plus 2025 has to be bigger than 2025. Okay, so solving that, well, that's pretty simple. It just means x is bigger than 0, right? That's simple, right? So does that mean anything can work? X could be 1,000,000,000 and this still works? No, unfortunately not, because actually this is our built-in assumption that x is going to be less than 2025, right, in order for it to have this shape. So actually, there's this other condition. In fact, 0 has to be less than x, has to be less than 2025. And now we can count the number of values of x that are positive integers that satisfy this condition. Well, it's everything from 1 to 2024, so there are 2024 of these. And so I'll write 2024 in this box. That's how many are in this case. Then there's just one more case here. I'll call this XX in 2025. And so in this case, we have to have x plus x is bigger than 2025, which means 2x is bigger than 2025, or x is bigger than, let's see, 2024 over 2, which is 1,012, something like this. And okay, again, can like 1,000,000,000 work? No, because it has to be less than 2025. So anything from 10, oh, actually greater than or equal to, anything from 1012 to 2025, which is, I think, okay, I'm going to write it out. 2025 minus 1012 plus 1. Actually, 2024 minus 1012, which is 1012 plus 1 is 1013. Okay, 1013. There's 1013 of these. Okay, quick math. And then 1013 plus 2024 is 3037. Okay, I believe that's D. William, do you agree with me?
No, just real quick, I think there should be 1013 instead of 1012, but otherwise that should be correct because we got 2024 cases from here. If we do the recalculation here, it would be 1012 cases. And
Oh
then
yeah, you're right.
finally,
You're right.
there's that
You're right.
one
You're right.
super
Oh yes.
special case
Okay. So
of
I
the
got the right answer
equilateral
by
triangle.
mistake. Yeah.
Totally forgot about that equilateral triangle at the beginning, and that will give us an answer of D.
Okay. Awesome. Yeah. So this is the classic example of math where you make two mistakes and they cancel out, and then you actually you got the right answer at the end. But yes, thank you, William, for pointing that out. Somehow I still did get the right answer, but yeah, maybe not for the right reasons. Okay, William, you want to maybe make fewer mistakes and take us on to the next question?
Yep. So Eli was really lucky that there were no two answers that were like consecutive for that problem because sometimes the AMC does that to try to trick you into clicking the wrong answer from a silly mistake. But here we can see that there are multiple answer choices that are off by one. See 15 and 16 and 44 and 45. So let's see if we can be a little more careful to this problem, not succumb to Eli's fate. So you consider the numbers 1, 2, and then 1, 2, 3, and then 1, 2, 3, 4, 3, 2, 1. Ooh, and that's 1, 2, 3, 4, 5, 4, 3, 2. So what I'm seeing in this problem is this sort of like hill pattern, right? You have a hill here. This is like 1, 2, 1, and then 2, 3, 2, 1, and then 2, 3, 4, 3, 2, 1. And then this hill just keeps getting bigger and bigger as we move on. And as Eli highlighted on his screen, something that's very interesting to look at is the base of these hills or mountains, whatever you call it. I think mountains is better because it's pointy. So I'm gonna look at, I guess, how much width each mountain has. So to get from this one to this one, you take 2 steps. So I'm gonna make a bracket here and say that this has 2 numbers in it. And then to get from this one to right before this one, we're going to have 4 numbers in it. And if we keep continuing this pattern, we're going to have 6, 8, and so on. So we want to find the 25th term in this sequence. Now, this problem is actually somewhat computationally intensive, but the idea is to try to find the number of hills such that the width is going to be somewhere, the total width is going to be somewhere near 2025. So let's say we we travel along K of these hills, right? Then that means their widths are going to be 2, 4, and all the way to 2K. Now, if you know about triangular numbers, you might know this formula. This is going to be 2 times 1 plus 2 plus 3 plus all the way to K. And the formula for that, 1 plus 2 plus all the way to K, is going to be K times K plus 1 over 2. If this is unfamiliar, then you could look up triangular numbers, and there's actually a really nice proof for this. Anyway, this will give us K times K plus 1. And remember, we want this to be approximately 25. So we want like a ballpark estimate of how many mountains we're going to have. And let's see. This is going to be somewhat around K squared, right? And 2025 is famously known for being equal to 45 squared. And this is something that you can obtain from a lot of practice. So this is going to be greater than K squared equals 45 squared. So how about K equals 44? K equals 44 times 45. This number is going to result in 1980. Right? I didn't mess. I think this is correct, right, Eli?
Yeah, I happen to have n minus 1 for a different reason. But yeah.
Yeah. So this step is like the big step. We went through most of the mountains already. So after 44 of these mountains, K equals 44, and then after 44 mountains, we would have went over 44 times 45 equals 1980 of these small numbers. So that means that the 1980th number is going to be the ending of a mountain. So it's going to end in a 2. So the 1981st number is going to be 1. We're at the beginning of a new mountain. 1982 is going to give you 2. And then all the way to 2025. 2025 is going to give you 45. Right, Eli?
Wait, okay. So it's just gonna be the difference between that and 1981 plus 1, right? So let's see, that's 44 plus 1, which is 45. Yeah, that's right. And okay, the only thing we have to make sure of, this is actually tricky, right? Because you don't know if it goes backwards or goes forwards first. But here we're at the 40. Okay. Does it stop at 45 or 44? That's my question.
Ah, yes, and that's a good point that Eli brings up, right? Like after 45 steps on our mountain, are we going to be somewhere here? We're going to be here? We're going to be here? Or are we going to be already going downhill? Now, as we notice, our first hill is going to have a peak at 2. Our second mountain has a peak at 3. Third one has a peak at 4, and so on. Meaning that our 45th mountain, which is the one that we're scaling, is going to have a peak at 46. So after 45 steps, we're gonna just barely be at the peak. So the answer is indeed 45. And let's just double check that. Yeah.
Okay, that's right. That's just so tricky, man. Like they're clearly trying to mess you up here. Because what if you thought it was like the 44th, and then you would think, okay, after 45, we're actually already back down to 43 or something. That's so tricky. Okay. It's okay. We got the right answer. William's the genius here. Let's go on to question number 6. We have an equilateral triangle. Each interior angle is trisected by a pair of rays. Interesting. I wonder how they trisected it. You know, this is actually a theorem that it's impossible to trisect an angle, or like a general angle. That's kind of interesting. Using ruler and compass. Okay, we have each interior angle is trisected by a pair of rays. The intersection of the interiors of the middle 20-degree angle at each vertex is the interior of a convex hexagon. Okay. I'm just going to draw the rays first, because I can't figure out what that's saying. Here we go. something like this. Um, the interiors of the middle 20-degree angle at each vertex. The middle 20-degree angle, so that's this angle here, right? These three angles are all 20 degrees. The interiors of the middle 20-degree angle at each vertex is the interior of a convex hexagon. Um, Okay, so this is a very bad drawing, and this is supposed to be a hexagon. So that's what I've been told. So this is the hexagon in here, and there's some stuff going on. Let's see. Oh, I can kind of see this hexagon. It's like this. I'm sure it's symmetric, but like this is the hexagon. 1, 2, 3, 4, 5, 6. Yeah, that's a hexagon. Something like this. What is the degree measure of the smallest angle of this hexagon? Okay. What a horrible question. I can't even comprehend it. Let's see if we can figure it out. So smallest angle in this hexagon. I feel like there must be a better way to draw this picture, but I don't know. I hope that are there some lines that like should be intersecting that are not intersecting? I'm not sure. Hopefully it doesn't matter too much. First of all, like certainly there's only going to be two different angles in this hexagon just by symmetry because there's rotational like 60-degree symmetry or 120-degree symmetry. So there can only be two angles and they have to be repeated here and here. So like there's some angle here, some angle here. Those are the only two different angles. What else can we glean from this? I think William's trying to help me out by drawing a better picture.
Yeah, so Eli's diagram is like really cluttered, and
Yeah,
I hate to break it to you, it's not very easy to read. But
yeah, I agree.
how about, but Eli did make a really nice observation. He said that many of the angles in the hexagon are going to be the same. So I thought to myself, how about we just focus on one of the angles,
Mm,
and then we can like apply that same angle to the rest of them. See,
yeah,
I think it's a little easier to work on this, hopefully a little easier to work on this diagram, right?
it should definitely be. Yeah. Okay, so looking at the diagram on William's screen, I think we actually know a lot of angles in there already. So we know the 20-degree angle at the top, of course, and we know the other two 20-degree angles. And we know those angles are also 20 degrees. And so that gives us, like, for example, this angle here, we can get using that, which gives us this angle in here. And that's already one of the angles that we wanted, isn't it? I think. Yeah. I don't want to draw it on my diagram because it's way too complicated. So yes, that gives us 180 minus 20 minus 20, which is 140. And so that gives us a 140-degree angle there, which I believe is already one of the angles that we wanted in our hexagon. I think it's one of those. And then
Yes.
we have, well, yeah, then it should be easy from here because we know that the sum of all of the angles in the hexagon is 180 times 4. We know that 3 of the angles are 140, and then we just divide by 3 to get the other one. And so that gives us something. Let's see, that's 3 times 40 plus 180. So 3 times 40 plus 180 divided by 3, which is 40 plus 60. I believe it's 100.
It looks about right to me. You want to see if the
About
answer's
right?
right?
Yeah, let's see if it's right. Okay, 100. Hey, cool.
Okay, yeah.
Okay.
Thank God.
Thank you
Yeah,
for
that's
drawing the picture. That was very
a
necessary,
bit of
William.
a
Okay,
yeah.
nice
I think
job.
without the
Okay.
picture, it might it might be a little tricky. So yeah, guys, draw big diagrams, or else you might mess up on a few of these questions. Now
Okay.
let's take a break from that geometry, and we're gonna have a nice, refreshing algebra problem. So have A and B are real numbers. Now, when this cubic polynomial x cubed plus x squared plus ax plus b is divided by x minus 1, the remainder is 4. Now, when the polynomial is divided by x minus 2, the remainder is 6. Now, we want to find b minus a. So, there's a really nice theorem in algebra called the remainder theorem. And essentially, that says that the remainder, when this is divided by this, is going to equal to the value when you plug x equals 1 into this polynomial. And there's actually a really quick proof for this. So suppose x cubed plus x squared plus ax plus b equals x minus 1. times a quotient polynomial that we don't know plus a remainder. Well, we know the remainder is going to be constant since we're dividing by a linear factor. Now, when you plug in x equals 1 on both sides, you'll see that this is 1 cubed plus 1 squared plus a times 1. Well, that's just equal to a plus b equals 1 minus 1 times cube x. But what is 1 minus 1? That's just 0. So this thing is just going to be completely obliterated, and that leaves us with r. So this means that the remainder, when you divide it by 1, is going to be 1 plus 1 plus a plus b equals 2 plus a plus b. And we're given that this is equal to 4. And we can do the same thing for x minus 2. This time we just plug in x equals 2. So this will give us 2 cubed equals 8 plus 2 squared equals 4 plus 2 times a equals 2a plus b equals 12 plus 2a plus b equals 6. And now it's just a matter of solving the system of equations. We can first simplify this and get a plus b equals 2, and 2a plus b equals negative 6. Yes. After you subtract a minus b from 2a plus b, you can get, 1 second, 2a plus b minus a plus b equals negative 6 minus 2 equals negative 8. And the left-hand side is actually going to equal a. Therefore, a equals negative 8. And from here, you can get b equals 10. b equals 10. And finally, what does the question ask for? It asks for what is b minus a? Now, 10 minus negative 8 is going to give us an answer of 18.
Nice job. Yeah, I think that's good reasoning there. A nice, simple algebra problem for us. We didn't have to draw any messy pictures. Really, really nice. Okay. Now we're on to number 8. Oh, it's logical. I love these kinds of problems. Okay. Agnes writes the following 4 statements on a blank piece of paper. At least one of these statements is true. At least 2 of these statements are true. At least 2 of these statements are false. At least 1 of these statements is false. Each statement is either true or false. How many false statements did Agnes write on the paper? Oh, I love these kinds of things. Okay, here we go. Okay, the first one, at least one of these statements is true. Okay, if that is true, then it doesn't contradict itself. So that's fine. If it's false, then it also doesn't contradict itself. So let's see if there's anything else we can say. At least 2 of these statements are true. If that's true, that would be fine. So, okay, these can't both be false. Let's see. At least 2 of these statements are false. If that were true, then 2 other ones would have to be false, which is interesting. And at least 1 of these statements is false. So, okay, that doesn't really help with anything. What's interesting about this is, like, if at least 2 of these statements are true, then at least 1 of these statements is true. So if this is true, then this is also true. And if this is true, then this is also true. So that just can't be the case, I think. Well, certainly they can't all be true, because then that would not be right. So let's see. How many false statements did Agnes write? Okay. Well, we know it's not 0, because we can't have all of them being true. I think there's nothing else to really do but just doing cases. I'm not sure if there's like a really, really clever way to do this, but I would just do cases on whether these are true or false. Because if this is true, then we know that this is true. And if this is true, we know this is true. Maybe there's some clever way. There is a clever way. There's a clever way, according to someone in the chat. I don't think Kevin. Oh, I don't know. I don't see the clever way. Okay, I'm just gonna say, yeah. William, do you have a clever way?
I might have a little better thing to do casework on. So I'm noticing that all of these statements are talking about the number of statements that are true, or the number of statements that are false. So when I'm looking at this,
Okay.
I want to translate this into numbers, because math is all about numbers, right? So let's say we have Q statements that are true. Now, the first one says at least one of them is true, meaning Q is greater than or equal to 1. The next one says that at least 2 of these statements are true, which means Q is greater than or equal to 2. The next one says at least 2 of these statements are false. Meaning, okay, so if we have Q statements that are true, then how many statements do we have that are false? It's going to be 4 minus Q. So that means that 4 minus Q is going to be greater than or equal to 2. And that will give me Q is less than or equal to 2. And then at least one of these statements is false. That is going to translate to Q is less than or equal to 3. And now we can just run through all possible values of Q. Is it 0? Is it 1? Is it 2? Is it 3? Is it 4? And the answer is going to be the 1 such that exactly Q of these inequalities hold. What do you think about that, Eli?
Yeah, that's a much better way. That's a cool way. Okay. So yeah, if Q equals 0, then what happens? Then that would mean they're all false. But that can't be the case, because if this is false, then that would mean that like at least 3 of them are true or something. So that can't be. So certainly Q is not equal to 0. We can just try Q equals 1. If Q equals 1, then this is true, this is false, this is true, so it's not equal to 1. We can get rid of that. Q equals to 2. We can look here, this is true, this is true, this is true, this is true, so there's too many that are true, so that doesn't work. Q equals 3. That would be true, true, false, true, and that works. So I believe that the answer should be 3. We can also just check to make sure. Q equals 4. We already mentioned they can't all be true. But yeah, Q equals 4. This is true, this is true, this is false, and that doesn't work. So we can get rid of all of these answers, and the answer must be, or how many false statements? Okay, sorry. How many false statements? 3, right? How many true statements? It was 3. The number of false statements was actually then 1. So we can get rid of those ones, add back these, and the answer should be 1. Okay. I believe the answer is B, which is 1. Okay. Am I correct? Thank God I am. Thank you, William, for your help. I think I'm probably going to need your help on like every question. So yeah, feel free to keep on helping me.
The question is scary. Oh dear, this question also looks a little scary. So our next question is going to be, we're given this, it's another cubic. Now, how many real numbers does the graph of y equals fx minus a pass through the point 125? Ooh, okay. So just a quick refresher for some algebra. X minus a, this is going to equal a shift of a units to the right. So we can take like a function that looks like this, and then we can move it this direction. And a can also be negative, so this could also technically be a shift to the left. So it's just any horizontal shift, essentially. So let's see. What would we do here? Now, suppose we had a point here that hit the line y equals 25. Now we want to shift this point to have an x coordinate of 1. And there's only one way to shift this graph, a graph with y coordinate 25 on this, a point with y coordinate 25 onto the point 125. However, let's say instead our graph looked more like this. Now we have 3 points on the graph that have a y coordinate of 25. So now once you shift this graph, there are 3 possible shifts that will put a point onto 1, 25. You can shift this point to 1, 25. You can shift this point to 1, 25. And you can shift this point to 1, 25. So it seems like, so that's going to give you an answer 3. Seems like the answer is going to be the number of points on this graph that have a y coordinate of 25. And it seems like many people are putting an answer choice of C. And let's just see if that's going to be correct. So what is our Cubic again is 100x cubed minus 300x squared plus 200x. All right. So let's take a crack at making this graph. Might be a little difficult, but as x is a very, I guess, very negative number, this graph is going to start from the bottom in terms of y-axis. And first of all, I'm going to factor out the 100. It will make things a little easier. X cubed minus 3x squared plus x. There we go, right? Oh, you can actually even factor this further. So this is going to be 100x times x squared minus 3x plus, oh, this is 2x. 2 after you take out the x. X squared minus 3x plus 2. Wow, sorry guys. Equals, and you can factor this quadratic as well. This is going to be x minus 1, x minus 2. So just from this factorization, you can notice where this is going to cross the x-axis. It's going to cross at -2, -1, and 0. So we already have a rough idea of what this graph is going to look like. But it's still a little difficult to find where this will cross y equals 25. We don't know if it's gonna, the line could be up here or it's gonna be down here. Let's just say it's down here where it intersects it 3 times for now. And Eli, how would you put the 25 into the question?
Okay, that's a good question. But let's see, I would probably try to approximate like at least one value that satisfies 25 equals to this, and then see where it lands, and then figure out where this is. Maybe that's not the right approach. I'm just thinking, because you know that the roots of this are 0, 1, and 2. And so if you know that it hits 25 somewhere like in the first hump, then you can know that it hits it in the other two. That would be what I was thinking. I was also wondering if you could use calculus to do this, and I was just thinking about that. But I feel like that's way too complicated. Let's not do that, yeah. So anyway, let's go with your approach. I was just going to see if another approach works. But yeah, since this polynomial factors so nicely, I think this is a much better way.
Yeah, the roots are 0, 1, 2. I said 0, -1, -2 by accident. It's 0, 1, 2. But anyway, let's just try like a number between 0 and 1, like 1/2. What will 1/2 give us? This is going to be 100 times, okay, 100 times 1/2 times -1/2 times -3/2, right? The reason I'm picking 1/2 is it seems to be like the peak in this hump, and I want it to cross or not cross 25. And this number is actually going to turn out to be greater than 25. So that means that this line is going to intersect this hump twice, and it's going to intersect this part one last time. So yes, in fact, the answer is going to be 3 and not 1. And let's just check. There it is indeed 3. All right. So yeah, this problem is a little annoying to prove rigorously that it intersects this graph 3 times instead of 1. But you can see that after some experimentation by playing with substitutions like x equals 1/2, you will get the answer.
Yeah. I think also you had to just notice that this polynomial factored super nicely, and so it was actually possible to graph. The reason I was mentioning calculus is because like calculus is a way, it gives you tools to graph weird functions like this and tells you where like these humps happen. But yeah, we didn't need to do that this time, luckily. So that's a nice solution. Okay, question number 11. We have a sequence that's arithmetic and a sequence that's geometric, and they're both strictly increasing and only contain integers. Ooh, that's interesting. And also z is as small as possible, z being the last thing in this arithmetic sequence. Now, what is the value of x plus y plus z plus p plus q? Interesting. Oh yeah, the interesting thing here is that z is there twice. Okay, so that's why I was wondering, like, this is just a random geometric series, but no, z is there twice. Okay, so let's see, what can we glean from this. They both start at 1. I mean, I'm thinking, do we just use like let's say the common difference is A, say the common ratio is R. That might be fine. So yeah, let's say this is A, this is R. You can't see the R, but this isn't R. And so then that means that like sequence 1 plus A, 1 plus 2A, and Z would be 1 plus 3A. And then this sequence would be 1, R, R squared, and R cubed, which is nice. And all of these are integers. And they're also increasing, so that means R is bigger than 1, and A is bigger than 0. Okay. And Z should be as small as possible. So the point is that we want to solve the equation 1 plus 3A is equal to R cubed in such a way that both of these things are as small as possible. And well, I mean, we can just minimize A because that's the same thing as minimizing Z. So, okay, if we just try R equals 1, I mean, that gives A equals 0, so that doesn't work. R equals 2 is 8. 8 minus 1 is 7. That's not divisible by 3. Can't be 3 because then you'd have 2 3s here. Can't be divisible. 4 cubed minus 1. Hey, that's going to be divisible by 3 because I can actually factor out 4 minus 1. That's cool. So we can just solve 1 plus 3A is equal to 4 cubed. 4 cubed, well, yeah, I said the cool factorization thing, so I'm not even going to calculate it, okay? This is 3A is equal to 4 cubed minus 1, which is 4 minus 1 times 4 squared plus 4 plus 1. Okay, and then 3 and 4 minus 1 cancel. So A is equal to 4 squared plus 4 plus 1, which is 16 plus 4 plus 1, which is 21. And now I think we're home free. We know that R is equal to 4 and A equals 21. And we just have to add some stuff up. Okay, that's going to be a joy. X plus Y plus Z plus P plus Q. That's going to be 4 plus 8 plus 16, which is 28. Okay. Oh, no, that's the P plus Q. Okay, whatever. That's 28. And then X plus Y is 1 plus 22, or there's no 1 there. It's just 22 plus 21 plus 1 plus 1. Oh, I'll just do it that way. 42 plus 1, which is 43. 43 plus 28 is 51, 71. That's not there. What did I do wrong? Oh, that's why.
These are
Yeah,
numbers
because
I
I
got.
just, yeah. Z is 64. I don't know what I was doing. This is 4, 16, and 64. I think I said something else entirely. 4, 16, and 64. That's 20 plus 64 is 84. 84 plus, and I was correct before in saying 43. 84 plus 43 is, no, I'm not right, am I? Ah, God. Okay, I just can't do this stuff in my head. I don't know why I keep trying to. Okay, here we go. We have 1 plus 21, 2, 1 plus 1 plus 21. Oh, that's why, because the 21 happens 3 times. Oh my God, okay, this is fine. 1 plus 42, and then we have 4, 16, and 64. So this is 84. This is 63 plus 2 is 65, plus 65. 69 plus 80 is 149. Okay, that's an answer choice. Great. It's E. Am I correct?
Yeah.
Yay. Okay. Wow. You know, I actually like the problem itself was fine. It's just actually calculating stuff. It's a nightmare. Anyway, on to you, William.
Yep. I'm sure that at this point that they're just trying to exhaust you. Well, let's see. Next question. Oh, it's combo now. So 6 chairs are arranged in a table. Now 2 students and 2 teachers randomly select 4 of the chairs to sit in. Now, what is the probability that 2 students will sit in 2 adjacent chairs and the 2 teachers will also sit in 2 adjacent chairs? So when it comes to this problem, you want to know a simple trick. And that trick is that it doesn't really matter. The order in which the students and the teachers sit in doesn't really matter, since these events are independent of each other. The student is not going to actually no, it's somewhat dependent, but at the end of the day, you can still do this because how do I explain this? Okay, so probability is like number of satisfactory ways over the total number of possibilities, right? So like when we try to find the number of satisfactory ways, we try to find two seats for the students and two seats for the teacher, such that the two students are next to each other and two teachers are next to each other. So let's see, how many ways are there for the two students to be next to each other? The two students can sit in these two seats, these two seats, these two seats, and so on. So there's 6 possible pairings that the students could sit in. And the thing is, student A can sit here and student B can sit here, or student B can sit here and student A can sit here. So in fact, there are going to be 12 possible places that the students sit in, right? And now what's left for us is the teachers. So let's just say the students occupy these two seats, and now we need to deal with the teachers. Now the teachers can sit in these two seats, or these two seats. So that's going to be 3. And then again, if teacher A sits here and teacher B sits here, that's different from teacher B sitting here and teacher A sitting here. So that's going to be another times 2. Now our denominator is the total amount of possible seatings. So remember, our characters' names are student A, student B, teacher A, and teacher B. And as I said, the order in which the students pick the chairs don't really matter. So we can just say that student A gets to pick first. Student A has all 6 chairs open to him. And then student B, they're not going to sit on top of each other. So student B has 5 seats left. And then teacher A has 4 seats left. Teacher B has 3 seats left. Now, after you do all these cancellations, 12 is equal to 4 times 3, so we can get rid of that. 3 times 2 equals 6. This is going to give us 1/5. All right, let's see it. Yeah, all right.
Nice. And there was a question, do we have to divide by rotations? Actually, no, we don't, because this is just like any 6 seats in a room. The fact that they're in a circle doesn't really matter. It only matters in the fact that the ends are like adjacent to each other again. Yeah, it's just the number of good ways over the number of total ways. And yeah, if they said like 2 ways of sitting are the same, if they're like you can rotate one to get to the other, then you would have to do something with rotations, but they don't say that. So hopefully that answers your question. Okay, on to the
Probability is
question.
hard.
Yeah, it is very confusing. There's a probability class that I've been told is really weird at school that I'm going to, because it's just like very abstract math, because actually even defining what probability means in an abstract way is like really hard. Because what does it even mean to say that something is random, Anyway, question number 16. There are 3 jars. Each of 3 coins is placed in one of the 3 jars, chosen at random, independently of the placements of the other coins. What is the expected number of coins in a jar with the most coins? Okay, so now we have to do probability again. Well, expectation, which is even worse. Okay, here we go. 3 jars, 3 jars. Jar A, jar B, and jar C. Well, I don't have to write the letters. Each of 3 coins is placed in one of the 3 jars, chosen at random. Okay, so they can be placed in the same jar if they wanted to. What is the expected number of coins in a jar with the most coins? Okay, so I would probably split this into cases as to how many coins are in a jar with the most coins. If it's 3, then you like find the probability that happens, and so on. So let's just do that. So let's say that the number is equal to 3, which means that the most coins are actually 3, like they all got placed in the same one. Well, okay, let's see, what's the probability of that happening? Well, the first coin is placed in some jar, and I really don't care what jar it is. It could be the first jar, it could be the second jar, it could be the third jar. But all I care about is that after that, the next coin and the next coin after that are placed into the same jar. What's the probability of that? Well, it's 1/3 to be placed in that jar, and then 1/3 again. So I believe this is a probability of 1/3 times 1/3, which is 1/9. Okay, hopefully that's right. Next, we can say, okay, is the biggest number actually 2? And then I don't think well, yeah, the number equal to 1 is much easier. So yeah, this is going to be the hardest case. Again, I don't care where the first one is. So let's say that the first one is in the first jar. And it's all symmetric, so it doesn't matter. Let's say that there's a coin in here. Okay, so we want to have, at some point, a jar with 2 and a jar with 1. Actually, maybe we shouldn't just say that the first coin is in here. Maybe we could just calculate the number of ways to have 2 and 1, and then divide by all the ways. Let's see, which is going to be easier. Actually, I think this will be just as easy. I think it'll be fine. So there's 2 ways that this could happen. One is that one of the coins goes in here and the other coin goes in there, one of these 2. So that would be 1/3 times 2/3, or 2/3 times 1/3, because it could happen either way. So there's 2 times 1/3 times 2/3. And I think that's there's only one more way, which is that neither of them go in here and they both go into one of these. So 2 times 1/3 times 1/3 plus 2/3 times 1/3. Okay, it's just 3 times 1/3 times 2/3. Well, fine. Yes, I believe this is right. And so this will just be 3 times 2/3 times 1/3, so it'll be 2/3. Okay, and then the last case is that the number is equal to 1. And okay, we can actually find that just from seeing it has to be 1 minus a ninth minus 2/3, but let's just make sure. So there would be all 3 just across the 3 here. There's only one way for that to happen. Well, okay, I guess there's 3 ways for that to happen. It's like 1/3 times 1/3 times 1/3, but the order doesn't matter, so it's like times 6. So anyway, it's 6/27, which is indeed 2/9, I believe. And that's exactly what it should be, because 2/9 plus 1/9 is 1/3 plus 2/3 is 1. So we're happy. In fact, I think actually an easier way you could have found this probability is by finding this probability and then subtracting. So, okay, well, yeah, if you were clever, you could have done that. But all we have to do now is add up, the product of the probability and the number, and then we'll find the expectation. So that's another calculation. You know how much I love these. Here we go. 1/9 times 3. That's 1/3. I'm pretty confident. 2/9 times 1. That's 2/9. I got this. 2 times 2/3. That's 4/3. Great. Okay. Then this is going to be 12 plus 3 is 15 plus 2 is 17. 17/9. Circle it. D. Is this the right answer? Yes. Oh, feels so good. Feels so good. On to you, William.
Hey, after all that combo, it's really nice to see a number theory finally. So let n be the unique positive integer such that dividing this huge number by n leaves a remainder of 16. And dividing this huge number by n leaves a remainder of 15. All right, so what is the tens digit of n? All right, so let's do it this way. We know that 273436 is equivalent to 16 modulo n. And if people are not familiar with modulo, in other words, you can write 273436 as some number times n plus 16. Basically, 16 is the remainder, right? And the same thing, you can do the same thing for the other huge number. We have 272760 equals y. We'll use a different number from x times n plus 15. Now, an interesting property about modulo is that you can subtract 16 from both sides, and you can do a lot of similar math that you do, similar arithmetic that you do in general. But I'm going to use these equations now that I wrote them down. I'm going to subtract this from this and also this from this. And this number minus this number is going to equal, let's see here. This is a little bit of mental math.
I think I did it.
Try
I
my
think it's
best.
676. I mean, okay, I shouldn't be the one to do this, but I'm pretty sure it's right.
Yeah.
Yeah.
Okay, equals x minus y times n plus 1. Right? Yeah, I knew the chat was gonna go wild when I saw this number. But anyway, let's go back to the problem. You guys still have your lovely 6, 7 number here because subtracting by 1 only changes the units digit in this case. Anyway, 6, 7, 5, 6, 7, 5, 6, 7, 5 equals x minus y times n. So this means that n has to divide 6, 7, 5. And how are we going to do this? Well, we want to find the prime factorization of 675. I'm going to start saying that from now on. This is going to equal, this is more mental maths for me. Come on.
Yeah, you can
It's
actually do it
40,
though. Like, yeah,
it's
I have to write it
5
down.
squared times 47, right?
Uh, it's 5 squared
No, that's not
times.
right.
It's
That's
definitely
not
not
right.
47. 47 is way too big. Wait. Uh, it's whatever 135
Um,
divided by 5 is. That's
it's
what 27. 27. 27.
27.
Yeah,
Oh,
yeah, yeah.
okay. That's a little better, I guess. I'll write
That
it
actually makes
this
sense.
way.
3 cubed times 5 squared.
3
Like, that's a
cubed
nice
times
number.
5 squared.
Yeah.
Okay, I think I get it. So remember that we do have a few precautions on us. N is a 2-digit number,
Mm.
right?
Well, it has a
And
tens digit. Yeah.
yeah. Um, and the thing is, when we took these two equations and subtracted it from each other, we also lost a little bit of information because now we know that the difference between these two remainders is 1, but we don't have any info about the original remainder. Like if this was 3 and this was 2, 3 minus 2 is still going to equal 1, and it's still going to divide this. So we still have to do a little bit of testing. Let's see here. Let's list out some prime factors. I mean, not prime factors, some divisors of this number. In total, there are going to be 3 plus
Mm.
1 times 2 plus 1 equals 12 divisors. So let's just list out a few. I know the single digits don't really count since n is 2 digits, but I will do that anyway.
Mm.
15. Next is what, Eli? 25, right? Yeah,
Yeah.
25.
I think you can actually get to the
27.
answer much quicker from here. Um, if you just look at the two numbers here and you know that n has to divide like this minus 16 and this minus 15, just by doing like the sum of the digits thing, you know that actually both of those are divisible by 9. Um, so, but I probably not by
Hmm.
27. So anyway, and they're both divisible by 5, right? So I think it just has to be 9 times 5, which is, oh, that's not an option. So never mind. Maybe keep doing what you're doing. Okay.
All right.
Okay.
So I've just listed some of these factors, and I'm just going to say, first of all, since the remainder are 15 and 16, that means that n has to be greater than 16. So then none of these are going to work. And then also a little bit of, I guess, exploiting the multiple choice format. You can see that the test digit is going to be 0, 1, 2, 3, 4, which means that our number is going to be less than 50. So that leaves us 3 things to check. And as Eli said, 273436 minus 16 is going to be 0 mod. Wait, hold on a second.
It's
Oh yeah,
divisible by
Eli's idea
9.
is, yeah, that doesn't mean
There-
that n is going to be divisible by 9. That's the
That's
issue.
that's true. Yes. Um, but
So
actually,
let's,
wait. With all the answer choices, how could if 5 is not on here? How is this even
well, the
possible?
answer is either going to be
Oh,
2 or 4.
tens digit.
The
Oh,
tens
okay.
digit.
Yeah.
Right,
I don't know.
right.
I was thinking the ones digit because usually that's the thing they ask for. Okay. Um, tens digit. Yeah. So then that's fine. I
So
mean,
let's,
but like 45 works, doesn't it? So if it's a unique positive integer that has this property.
yeah, we could do 45, but let's just go through this a little more rigorously, right? So it's
Okay.
273436 is going to be equivalent to 16 mod n, which means that our big number minus 16, which is going to result in this is divisible by n. Now, if you know numbers that are divisible by 25, the last 2 digits are going to be 25, 50, 75, or 00. And that is none of the above here.
Mm.
So it's not going to be 25. So now it's just down between 27 and 45. So For 27, I think I could just do a quick check, right? First of all, we can eliminate the 27 at the beginning since this is 27 times extra 4 place values. So you can 27 3420 mod 27 is going to be 3420 mod 27. And what is this going to be equal to? After you do a little bit of long division, you should be able to get that this is not equivalent to 0 mod 27, which means that n is not going to be 27. So the only answer is going to be 45. This is a lot
Okay,
of computationally intensive questions that they're throwing at us. And oh yeah, the answer is not 45. The answer is the tens digit of 45, which gives you 4.
okay. So I was right before, but I thought that I had to be wrong because I thought it was the units digit. But yeah, whatever. Yeah, I think once you notice that this is divisible, like both of them are both divisible by 9 and 5 once you subtract the thing, then like n being 45 works. And so like yeah. Um anyway,
Yeah,
I
I
guess
see.
it
It
doesn't
seems like
doesn't like make that
a
much of a
lot of the
difference,
time
but
you're
whatever.
still going to need a lot of computation.
Yeah. And by the way, I think maybe something is unclear. Like, why doesn't like say 15 work? Well, having a remainder of 15, that would be a remainder of 0 if it was 15. So like,
Yeah.
for example, like that's why like you can't just remove factors because you still have to be bigger than like. Yes. Anyway, let's go on to the next question. We were right on that one. Oh, we have an array of numbers now. That's very interesting. We start with -1, 3, 1. And each adjacent pair of numbers is summed to produce the number in the next row. So is that like, oh yeah, it's like Pascal. This is fun stuff. Okay, 4 plus 1 and so on. -1 plus 3 is 2, 3 plus 1, 4, 4 plus 1 is 5, 2 plus 4 is 6. This is cool stuff. Each row begins with a -1 and a 1. Okay, so it's like the negative Pascal. Like usually Pascal's with all ones here and here, and they've made it weird. If the process continues, one of the rows will sum to 12, 2, 8, 8. In that row, what is the third number from the left? Oh, wow. This is some interesting stuff. I mean, my first instinct would be like, surely we can just find a formula for like the nth row, kth entry or something using some like binomial coefficients. And yeah, I mean, is there like a smart way? Um, Probably so, but I'm not sure what it is. Let's see. Like, if I just look at the sums, like this is 3, this is 6, this is 12. Um, and yeah, it's like vaguely, it's just multiplying by 2. Of course it is. Yeah, it's the same reason that it multiplied by 2 as in the regular Pascal's triangle, because when you're adding things up, you're just getting 2 copies of everything, and the -1 and 1 actually cancel. So the sum is always going to be 3 times 2 to the n. Okay. And 3 times 2 to the n is equal to 12, 8, 288. For some n, we can check that that's n equals something. Because this is what, 40, 96. So that's n equals 12. Yes, it is. Okay, so some here, this is when n equals 1, or n equals 0, right? N equals 1, n equals 2, and so on. So this is in the, like, what, 13th row or something, if this is the first row. Okay, does that actually help us? Maybe. Third number from the left. So that's these numbers here. The next thing I would try is like keep on writing down this table and figure out what the third number from the left is in general. So that's something that let's try. So we have -1. This will be 0, 7. So that's a 7 now. And should we need any more than this? Maybe. Let's just write out that one. That's -1, -1. You can't really see this, but that's okay. 7. So it's still a 7. I assume that's what it means by third number from the left. It's just like you count over 3. So 1, 4, 6, 7, 7, -1, 0, 6, -1, -1, 6, -1, -2, 5. Okay, so something interesting is going on here. Actually, I think we could literally just compute out what it is until the 13th row. I don't even think we have to do anything. Like this is going to take some time, but it's not going to take that long. It's really just decreasing by 1 a bunch of times. and then maybe by 2 and by 3. I don't know if, William, you see like there's a clever way. Do you see a clever way, or do you want to just like compute the row? It'll literally only take like 20 seconds to just finish this, especially if it was on paper.
Because the number we're looking for the 12th row, let's consider that this is a 0th row. I think it's better to write out everything. But I believe that there should be a quadratic function that will tell you, that will predict these numbers for you. And in
Yeah, that's
fact, you
true.
can
That's true.
wait. Yeah, I think for larger numbers, you would use uh
Yeah, it's just
the
3 to 1 0.
quadratic
Yeah.
representation, and I think this actually goes from 1 4 6 7 7 6 4 1. You'll see like there's like a symmetry. It kind of does like a reflection.
Yeah. I mean, it's something like -1/2 n squared, and then there's like some other factor here. Um, maybe it's -2n or +2n or something.
And albeit this is a little annoying to compute, we still need to get this question. So I think we gotta keep moving on. And
Gotcha.
you'll notice pretty quickly that this is actually just decreasing by 1 every single time. So 1, -3, 4, -1, -4, 1, -1, -5, -3. What row am I on? This is 0, 1, 2, 3, 4, 5, 6, 7, 8. So just 4 more rows to go until we are complete, right?
Hmm.
-1, -6, -8, -1, -7, -14. That's 10 rows, right? -1, -8, -21, and -1, -9, -29. So if you're a speedy addition problem solver, you'll get A equals 29, -29 somewhat comfortably. And I do have a quick explanation for why it is multiplying by 2 every single time. So you'll note that -1 will contribute to this row, the bottom row below twice, right? It will contribute -1 to this number, contribute -1 to this number. Same thing goes for 3. 3 contributes 3 to this cell, and 3 contributes 3 to this cell. Same thing goes for this one. So basically, every number in the row above will contribute twice, which means that the row below will be 2 times, the sum of the numbers in the row below is going to be 2 times the sum of each number in the row above. So that's if you keep doubling, 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 doubling. But of course, it's the AMC, you don't have to show that. So you could just do some experimentation and we'll get that result pretty quickly.
Yes, okay, I got it. Just making sure. I just did it with the actual formula. It's -1/2 n squared + 7/2 n + 1. You plug in n equals 12. You get -29, thankfully. Okay, yes. Anyway, that's the right answer. On to question number 20. We have a silo, a right. Oh, this is actually your question, isn't it? Is this Williams?
What is it? I think at this point, like, we're on question 20 already. Like,
Yeah, okay. I mean, we'll keep on
I think
working
we should
together
start
anyway, but
like working together more. Like,
yeah.
we've already been seeing this happening.
Okay, so but you want to read it? You can go ahead.
How about you read the question? Because I don't know.
You
I've
just
been
want
doing a lot of
me
talking.
to
I've been doing
deal with all the
a lot of
words.
talking today. All right. Okay. I'm not putting all the responsibility on your side. I will draw the diagram for you
Okay,
since
okay.
clearly I'm better at drawing diagrams than you, that right? Than you,
Yeah, it's just a lot of
right?
words. Like I have to read an essay to understand this question. Okay, we have a silo, a right circular cylinder with diameter 20 in a field. McDonald is located 20 meters west and 50 meters south of the center of the silo. McGregor is located 20 meters east and some number G meters south of the center of the silo. The line of sight between McDonald and McGregor is tangent to the silo. Okay, so we have some 3D tangency thing. That's pretty cool. The value of G can be written as A root B minus C over D, where A, B, C, and D are positive integers, and blah, blah, blah. That's just saying what the format of the answer is, and we have to find it. So we have to find this, this G here. Okay, I can tell, William, your drawing skills are coming in handy.
It's south of the silo. Okay. All right. This is gonna take a little bit of time
Yeah.
because actually, while I was drawing the diagram, I couldn't read the entire question.
Okay, I have it up on my screen. this is helpful.
Oh, the line of sight between McDonald and McGregor is tangent to the silo. Okay.
Yeah.
Yeah, this is gonna be a little hard to draw, but while Eli explains, I'll try my very best.
Okay. So, I mean, I don't know if I can really explain without some sort of diagram here, but we have McDonald McGregor, and we know where they are in relation to a silo. And I don't actually know, do we need anything three-dimensional, or is it really just because they're not up or down relative to each other. I think it's just, yeah, this is just a 2D problem. So we have something that's like 15 and then 20 and some other distance, some other distance. And we have a circle of a known diameter. And all we have to do is find this number G, which is how far in some direction this other person is in such a way that this line becomes tangent to this circle. So actually, I don't think we need anything three-dimensional. Luckily, it's just a 2D problem. Uh, and
Like, looks like I have to draw another diagram, do I?
well, at least we don't have to have the whole 3D silo in there, which is nice. It's
I
a
mean,
beautiful silo. You know, nothing against your silo, but I mean, I
I'll
think
draw
today
it.
we can just look at the silo from above, and
Yeah.
we won't have to
As
deal with it.
much as I loved my diagram, I think a 2D diagram, now that you read the whole question, I think a 2D diagram will be better in this scenario. So I'll work on that, I guess.
Okay. So we have the silo. I guess I'll just also try drawing it because I don't know what else to do. Let's see. We have a silo diameter 20. That means radius 10. Cool. And McDonald's located is 20 meters west, 15 meters south of the center of the silo. So west 20 and south 10, 15. Okay, sure. Somewhere here. So this is 15 and this is 20. Just imagine it's 20, whatever. Um, and then McGregor is located 20 meters east and some meters south. So east, so it goes like this. This is another 10, and G south. It's here, and then there's this tangency there. And we just have to find this G. Pretty simple geometry problem. I think it'll be okay. And yes, Williams is more to scale. I kind of ran out of space. Oh well. This is vaguely twice this, right? Looks like it. And so okay, my first instinct here would be to, I don't know, drop a perpendicular here and do something with that. Not sure if that's actually useful. The other thing would be to draw in this, yeah, as William already did, draw in this radius. I'm sure that'll come in handy. And we know that this is 10. Yeah. Anything else we can do that makes sense? I would probably draw like this line in because we know how to find like this length, and then we could find this length all in terms of G, right? I'm not sure if that's useful.
Hmm. So I do like Eli's idea of dropping this here, since remember, we're given a condition that this line is tangent to the circle, and whenever you have tangents, you always want to drop the center to that tangent point. But how do we go on from here? It seems like this is starting to get a little difficult. Well,
Well, I do see one
one I
nice thing. Yeah, go ahead.
let's see, let's hear your idea first.
Okay. Well, one nice thing is I see a 15 and a 20, and it's a right triangle. So like 3, 4, 5 all the way. That's great. So this has to be 25. That's really nice. Something that happens. And then that also tells us this length here, right? That's going to be whatever 25 squared minus 10 squared square root it is. Square root of 5, square root of 23.
525, right?
What? It's
525.
5 root 23, right? I think.
Oh yeah, you're right, you're right.
Yeah. Well, whatever. I mean, it doesn't matter how you phrase it. I think probably we won't
Yeah,
even
we don't
really
have to
need
worry
this.
about this at the moment.
Yeah. And then the other thing that I was going to say is to draw this in, and then we could find like both of these lengths. But that's not really super useful yet because that doesn't help us actually get G. Um,
5
so,
21, by the way.
but I'm sure this. Oh, it's root 21. Oh, sorry.
Yeah.
Yeah. That's right. And I'm sure that this 3, 4, 5 triangle has to be part of it, okay? Because there's never anything that nice without actually being used. So I'll just mention that. And now, William, you can go ahead.
I would like to counter that, since even though there's a 3, 4, 5, the answer is this form. So like, I'm sorry, Eli, you might have lived in a world where everything is 3, 4, 5 triangles, but now you have to face reality,
Mm.
and that G is not going to be a very good looking number.
Oh
All right,
well.
anyway,
Okay.
I had, let's see, I had like a little idea
Hmm.
in the back of my mind for a little bit. So, shoot, I didn't mean to change the whole color. Let's extend this line
Yeah.
all
Good
the
idea.
way here. And let's extend this all the way here. So I just had like a hunch that this could help us a little because the idea behind this is that here, with this line, we created a whole bunch of similar triangles. This triangle here is similar to this triangle here, is similar to this triangle here. And that's pretty helpful because like, okay, the reason why they're all similar is because they all have a right angle, they all have this angle here. And similar triangles are really good for these type of questions. And let's just see how we are going to approach this. It seems like Eli's 5 root 21 is going to come into play because, let's see here. If we take this length and then divide it by the hypotenuse of this triangle, let's just say that this length is x,
Okay.
right? 10 over 20 plus x is going to equal 15 over this huge length, which seems to be 5 root 21 plus, let's see, this is a Pythagorean. Okay, this seems to be really nasty at the end of the day as well, but
But I
hmm,
mean, it'll give us X, right? But it'll be bad.
it'll be
Uh,
terrifying.
uh, yeah. Okay. Um,
I mean, seeing the answer attraction, I think we might have to bear with it, right?
oh no. Well, at least we could call 20X like give it a name, and then this would be like a little bit nicer.
Oh, wait, that's a good observation. Good observation. Let's say this is, let's call it the very creative name of Y. All right. If it wasn't for Eli, I probably would have lost a few years on my lifespan. So good catch. And as a reward, how about you do this calculation, Eli?
Are you are you joking? Uh, okay. I guess so. So anyway, this is the bottom here is 5 root 21 plus, let's see. Yeah, you already did this question. Square root of y squared minus 10 squared. Yeah. Or y squared minus 100. Okay, cool. Um, and now we just multiply both sides, cross multiply. We have 10 times 5. So this is really 50 root 21 plus 10 root y squared minus 100 is equal to 15y. This is a nightmare. I mean, honestly, I don't know uh, if I want to do this. Is there, obviously we can get rid of some like fives and stuff, but like then we're gonna have to square both sides and then we'll have a quadratic. Okay, it'll actually be fine. It'll be fine. Let's just do it. Stop complaining. Stop complaining. Okay, so first I'll divide by 5. We'll get 10 root 21 plus 2 root y squared minus 100 is equal to 3y. I'll move this step over. 2 root y squared minus 100 is equal to 3y minus 10 root 21. I'll square both sides. I'm going to get 4y squared minus 100 is 9y squared minus 60y root 21 plus 100 times 21 is 2100. Great. And now this is just the most horrendous quadratic ever. Okay, so it's 5y squared minus 60y root 21. So minus 400 or plus 400 plus, so it's plus 2,500. Okay, wait, this feels like it should be fine. This feels like it should be fine. Because we can divide by 5. So we get y squared minus 12y root 21 plus 500 is 0. Okay. Did I do anything wrong? I hope not, because I'm going to use the quadratic formula, and I hope that
Oh,
it's
look
going
at
to
the
be interesting.
chat. Everyone's cheering for you.
Ah, yeah, I know. Okay, I know. This is a marathon, and I'm only like in the 3/8 mark or something. Okay, here we go. 12 root 21 plus or minus square root of this squared. 21 times 144. Okay, minus 2,000. Okay, all over 2. So that's 6 root 21 plus or minus something. Like who even cares? This is 21 times 144. Who knows what that is? 144 times 21 is 4410882 412 3024. So this is, oh my God, it's 1024. Are you actually joking? Wait, was there a way to factor this or something? Okay, well, I don't know. Oh, I didn't need to divide by 2. Never mind. Because I can divide by 2 inside. 1024 divided by 4 is 256. In any case, that's just, what is that, 16 squared? So this is 6 root 21 plus or minus 16. And it's going to be minus 16, or it's going to be plus, wait. Which thing is bigger, 36 times 21? Well, I guess we'd have to go back to the diagram, right, to make sure, to see which one is which, because I actually think this is still bigger than 16. So actually, oh, it can't be plus 16,
Remember
because
that
then it
it's
would
at
be,
least 20. Right.
oh, it's at least 20. Oh, yeah, so if it can't be minus 16, then. Yeah, that's right. So, okay, it's definitely plus 16. There we go, it's at least 20. So that means x is equal to this minus 20, which is 6 root 21 minus 4. This is horrendous. I mean, there's no way they expected people to do this on a test. Well, maybe they did, but this is just horrible.
So wait, you're not done yet, Eli?
I know I'm not done, but like, okay, okay. So we have x, and okay, I don't even remember what x was. Go back to this diagram, which is far away. And we have to find g. Can we just use similarity at this point? Is there a fast way?
I think similarity is the best way to do
Yeah,
this.
it's just g over 15, and then x over x plus 40, right? Is that the fastest? Yes?
Uh,
No, is it not?
I think so, yeah. G over x equals 15. G over x equals 15 over 40 plus x.
Okay, yeah, you can do it that way. G over, well, I want to do it the G over 15 way. I think it's also fine. Okay, whatever. I'll just write it as G over 15 is x, yeah, it's x over x plus 40, the way I'm thinking of it, because you're just using those two. And then this gives you G is 15 times, okay, well, this is 6 root 21 minus 4 over 6 root 21 plus 36, I think. And then we just have to simplify this. Why? This is so bad. Okay, so this is 5 times 6 root 21 minus 4 over 2 root 21 plus 12. We can multiply the top and bottom by root 21 minus 6, I think. This is 5, 6 root 21 minus 4 over 3 root 21, or 2 root 21. It's a 2. So it's a 2 all along. Plus 12, and then times root 21 minus 6. The reason to do that is that you'll get some cancellation, which is nice. So this will be 30. Well, yeah, let's just, and top and bottom, of course. So this is root 21 minus 6. Oh, okay. So the top, what's the top going to be? Let's just do the top. That's going to be okay, 5 times 6 times 21 minus 36 root 21 minus 4 root 21 plus 24. And then that's the top. And then the bottom is, well, okay, 2 times like 21 minus 36. Okay, so this is going to be negative, whatever. 2 times 21 minus 36. I'll just write it that way. Okay, so we have this big thing. We're almost there. We have, okay, this is 6 times 21 is 126 plus 24, 126 plus 24. Hey, that's 150, I think. So that's nice. So 5 times 150 minus 40 root 21 over 2 times 21 minus 36 is negative 15, so negative 30. You can get rid of some zeros. No 0 there, no 0 there, no 0 there. Make it positive, so this is going to be 20 root 21 minus 5 times 15 is something. 5 times 15 is, let's see, 65, 50, 65. Yes, no, it's
75.
75. Oh my God, whatever. 75. And then divided by 3. And that's the format, right?
41, 1.6.
Hmm.
Okay, that gives us 119. Yes, sir!
Wait,
Eli, you did
seriously?
it!
Oh my
My
God. Okay.
God, my man,
I
that's my
didn't believe
man.
I didn't believe this was possible, but we did it. Okay. I hope there's a better way, but like, so this works. So yeah, 20 plus 21 plus 75 plus 3 is indeed 119, I think.
I'm sure there's a
Uh,
better way, guys, but like,
oh my God.
uh, that's what we're
Okay.
gonna have to go with for now, I guess. Yeah, I think the point of that problem being that far in the exam is just for you to do a bunch of computations, because that answer does not look nice either.
Uh, okay. Well, hopefully the next one will be nicer. William, take it away.
Okay, I'll give you a little break, I guess, after that question. So, a set of numbers is sum free if whenever x and y are not necessarily distinct elements. So, x and y could be the same number. X plus y is not an element of the set. So, for example, 146 and the empty set are sum free, but 245 is not. Now, what is the greatest possible number of elements in a sum free subset of these numbers? Now, this type of question is actually somewhat common, and I can just show you a trick right now. So, you know how like an odd number plus an odd number is an even number, and it will never ever be an odd number? Even numbers plus even numbers equals odd number. I mean, no, oh God, even number plus even number equals even number. O plus O equals E, right? E plus E equals E, and O plus E equals O. So there's a interesting thing that you can do is that if you take all of the odd numbers in this set, so 1, 3, 5, 7, 9, and so on to 19, you'll notice that since no two of these numbers add, like whenever you take two numbers in the set and you add them together to get an even number, you'll get an even number, but there are no even numbers in this set. So that means that our answer is already going to be at least 10. So let's just get rid of 8 and 9 real quick. Now suppose that our answer is 11 instead, which means that there is at least one even number. Let's say we have one even number, and this even number is like 2x, right? But we still have 10 odd numbers, which is all of these. And one of these odd numbers is going to be, all right, let's see, this is like actually pretty annoying to explain. But if x is an odd number, we can't do that. Let's say like if x is 5, then 5 plus 5 is going to equal 2 times 5. And if this was like, let's say 4 instead, you'll notice that 1 plus 4 is equal to 5. And you'll see that like whenever you have an even number, there's just like so little, I guess, space. It's too airtight already. This is like, I guess, what do you say? It can't fit any more numbers, like especially the even numbers. So, like I say, mostly going off vibes, you're gonna get the answer of 10. Unfortunately, I'm not sure if I can
Wait,
think
wait,
of
wait, wait, wait.
the most
Wait,
rigorous
wait,
proof
wait.
on
I
that.
don't think it is. Maybe I'm wrong, but can't you add 20 to this set? Oh no, but then
No,
1 plus 19 is
yeah,
20.
1 plus 19
Oh,
equals
dang
20.
it. Oh my God. Okay, so I was
It's
thinking
way
like
too airtight.
yeah, yeah, I was thinking like 20, like 20 plus anything is bigger than 20, but no, you're right. Because you can get 20. I don't know. Is there a good way to prove this? That's a good question.
Yeah. See, oh
Yeah.
yeah, Ryan Guo also has another nice stat, which is 11, 12, 13, all the way to 20. So that will also work.
Hmm.
Wait, I might have a formal roof on me. Hold on. Okay. Like, oh, I don't know if we have time for this. Do you want to do another question first?
Yeah, we can like
Back to
come
this
back to
one.
this. I think there's
Yeah.
two more, maybe three more. So we're close to the end anyway.
Yeah.
Okay, number 23. Oh no, it's geometry. Okay, yeah, we see that I'm not the these are not my favorite questions, but it's okay. Triangle ABC has side lengths 80, 45, and 75, the bisector of angle B, and the altitude to side AB intersect at point P. What is BP? Okay, we need another picture. Picture time. We have 80, 45, and 75. Okay, so like 80 and 75 are like close. And then 45 is like a little bit shorter, something like this, maybe. So AB is 80, BC is 45. So let's say A, B, C, 80, uh, 45 here, and 75. And then the bisector of B and the altitude to side AB intersect at B. So bisector of B is like this. Altitude to side AB is like this. And they intersect at some point. The question is, what is B to P? B to this point. This is the point P. Okay. Uh, okay, I know how to do at least some things in this. I know how to find like this length here, this altitude. You can find using Heron's formula. You can find the area of the whole thing, and then divide by 2 times 80, and you'll get this. Or well, multiply by 2 and divide by 80, and you'll get this length. Not quite sure that helps. The other thing that I would think is to use the angle bisector theorem, which gives you some ratios. I don't know. William, what would you do? Do you see anything in particular? Because I honestly, okay, if I ever do something like this, it's just going to be super bashy like the last one. So
I
I'm
have
sure there
a
must be a clever
solution in
way.
mind, but it's super, super, super bashy. Not as
Okay,
bad
so
as P20, but like it's still kind of annoying. Like, I think, oh, let me try to think of a new solution. Our best bet, so we're trying to find BP, right?
yeah,
Um, so as Eli said, let's label this point E and let's label this point D for convenience. As
mm,
Eli said, it should be pretty easy to find CE, and and from that it should also be somewhat easy to find BE, right? And as long as we can find PE, then we should be able to get BP. Is that right, Eli? So I think a
yeah,
good
yeah.
first step would just to be find CE. Um,
Mm, okay.
I guess I'll do the honors of the calculations right now. Yeah, when it comes to lay AMC problems and also like lay AME problems, there's a lot of computation that you have to do, unfortunately.
One thing I want to do is just divide everything by 5 and then multiply by 5 again later. I don't know, maybe there's a 5 there for a reason, but like I like smaller numbers. So I'm just gonna
Mhm.
forget about this and make it 9,
Yeah, that's a
16,
good idea.
and 15.
9, 16, and
That
9,
just
15,
feels
16.
nicer to
Yeah.
me. Um,
Yeah, so like formulas like Heron's are going to be easier. So like the perimeter is 40, so the semi-perimeter is 20. So our area is going to be wait, hold on a second. How does Heron's? Okay, yeah,
24, 5,
20
11.
times 11 times 5 times 4. So even though we have a square root of 11, which is not nice, 5 times 4 is equal to 20. So our 20 is going to be moved outside.
Nice.
Now from here, we can get this altitude. Since this altitude times 16 is going to equal the area times 2. So this altitude is going to turn out to be, hold on a second. 16 times altitude equals, is 40 over, it's
Wait, is it not
5
just
root
like,
11 over 2, right?
Yes, that's right. Because it's just 2 times this, which is 40 divided by 16, so divided by 5 root 11 over 2.
Yeah, and from here, you should also be able to get BE from the Pythagorean theorem, right?
Yeah.
So BE
Mhm.
is equal to, yes, this question requires some computations, unfortunately. 81, the square root of, the square of 9 is equal to 81, and the square of C is going to be this. Yes. And this is going to equal, oh my God, 324 minus 275. 7 halves. Yeah, it seems to be. So that's at least we have a nice number on us. 7 over 2. And now, if we can find PE, we're pretty much set. The thing is, we know what CE is, right? CE is 5 root 11 over 2. And we also have the angle bisector theorem on us. So what fraction of CE is PE going to be? It's going to be 7 over 2 over 7 over 2 plus 9, right? This is how the angle bisector theorem works. And this will give us 7 over 25, right? Eli, is that right? 7 over 25?
Yeah, that's right. So, okay, I just like you do this so quickly in your head. It's amazing. Okay, 7 over 25.
7 over
Yes,
25.
times the original value you got for CE, which is 5 root 11 over 2, right? So yeah,
Yes,
something like
5 root 11
this.
over 2.
And
So
so it's
this
7 over
PE
10,
is
7
going
root 11 over
to
10, I think.
7 root, oh, yeah, okay. So PE
Uh,
is 7 root 11 over 10. All right, and now we can finally do the final step, which is just one application of Pythagorean theorem
hmm.
with silent 7 over 2 times 7 root 11 over 10. All right, so seems like this problem is more peaceful than the others. Oh God, what is going on with
Looks
my,
like our
my writing?
method of writing has been destroyed. Maybe we're back.
Um,
Interesting and
all right,
simultaneous. So this is not on our end. This is on their end,
yeah,
which
yeah,
is kind of
not our fault,
entertaining.
guys, not our fault.
um,
All right, so what
okay,
do
we'll
we
do it
do
in
in
our
this
head. We'll do
situation?
it in our head. So it's 7 root 11 over 2 and 7 halves, and we're finding the hypotenuse, right? So it's adding the squares, I think. You remember the
Yeah.
diagram? Yeah.
Yeah,
Okay,
yeah.
so
Oh, I just really
okay,
wish I could write down things. 7 over
okay,
2
so we can get the
squared.
7 out. We can get the 7 out, and it's 11. And wait, also the 2, right? Yeah. So 7 halves, and 11, 11 over like 100, and plus like 40 plus 1, right? 11 over 100 plus 1. So 111 over 100. Is this correct? Just imagining.
Um, let me try to do something else. Oh God, bored. Am I lagging out? Oh
Uh,
God.
Now I hear the music, so I think they're cutting us off.
Damn.
Oh, wow.
Okay.